All right, this brings us to our algorithm, first algorithm of the day, Prim's algorithm for computing the minimum spanning tree. So I'm going to do two demos. This alternate demo first. I borrowed this one from my old colleagues at Princeton, and it's going to be a conceptual explanation of how this works. Now, for some reason, it's smaller on the screen, so scoot in just a little. I'll join you. The way this algorithm is going to work is we're going to start with some arbitrary vertex. Here, let's say this is vertex 0, and we're going to greedily grow our tree t. What do we mean by that? Well, what we're going to do is at all points, we're going to add to t the minimum weight edge that has exactly one endpoint in the tree we built so far. And we're just going to repeat this process until we have v minus 1 edges. So starting from this point, right, we can color this vertex white. And because of the cut property, then, we're going to grab the smallest crossing edge, one of these four. Okay? So in that case, it's this edge right here. And so that gets added to the MST. Okay. Challenge for you. Which edge comes next? And I have all the weights listed here. Okay, so it's 1/7. The edge that connects 1 and 7 together comes next, and so we'll add that. At that point, we can form a new cut, which is everything that's part of the tree and everything that's not. Okay, so this is coming almost directly from the cut property, right? What we've done is we've found a nice way to construct cuts that steadily grow the tree. So rather than picking randomly, as I kind of proposed earlier, this is a simpler alternative. Okay, so next up comes, now all of these edges are in play. This is the shortest one, so we'll add that. Now all the edges are these two, this one, this one, this one, this one, this one, this one. Make sure that makes sense. Why is it exactly these edges in red? Okay, so next up, that's the smallest one. And so now the edges we're going to be considering are all of those which connect the white with the gray, which are all of these. This is the smallest. Okay, then these edges, this one's smallest. And then finally, these four edges where this is the smallest. And that is the minimum spanning tree. Okay, so that's a conceptual picture. Let's discuss how we might actually implement that in Java. Pause. So let's see that algorithm again in terms of specific data structures in Java. So in this case, what I'm going to do is I'm going to create a fringe. And that fringe is going to start out as just the start vertex. And each vertex is going to be given a priority. In this case, the fringe is a priority queue. And each vertex is going to be given a priority that is equal to the distance from the tree. Okay? So 0 is 0 units of distance away from the tree. So it's on there with priority 0. And then what we're going to do is repeatedly do the following. We're going to remove the closest vertex in the priority queue, and they're going to relax all of the edges pointing from V. Okay? So in this case, what we can do is we can say, is 2 better than infinity? Is 1 better than infinity? Yes. So I'll have a couple of arrays here, similar to what we did with Dijkstra's, and I'll set the distance to position 1 to be 2, and the position to 2 to be 1, right? In line with what these arrows say, or what these edges say. And then we'll also set the edge to. Okay? And at that point, we now have a fringe which has 2 vertices, this one being a little closer. So we'll relax this one next. Okay? So I'm going to make an observation here, which is that as soon as I relax this vertex, we know that this edge will definitely be part of the minimum spanning tree. That is, the edge 2 entry in the array of edge 2's, this will just never change, because how could it, right? There's no way that this could ever change from this point on. So I'm going to be demarcating that with a bold line here to say that this line is part of the minimum spanning tree. Okay? All right. And so now that we're relaxing this vertex, we can look at each of these outgoing edges, and we can do the same trick. We can say, is 5 better than 2? No. Is 1 better than infinity? Yes. Is 15 better than infinity? Yes. Now notice, the priority that I'm going to give to this vertex is not going to be 2, but rather 1. And the reason for that is we're trying to draw a spanning tree, not a shortest paths tree. We only care about the distance from the tree that we built so far, because we're kind of treating it like this, this cut idea. This is the white side of the cut. This is the green side of the cut. Okay? So after that relaxation is done, we're left in this situation. Okay? So what we can say so far is that the best known edge from 0 to 1 is this edge. The best known edge from 2 to 4 is this one. From 2 to 5 is this one. And from 0 to 1, the best edge is 1. Okay? And this one we're bolding in order to indicate that this is definitely locked in, and these may or may not end up being locked in. That is, this one we know will never change. It's bolded, but these maybe. They could change. Okay? We'll see how it goes. Alrighty. Next up, we look at the fringe and we say this is the most the lowest priority vertex, so it'll come first. And so what I'd like you to do now is think about what will be the distance to, edge to, and fringe after the next relaxation. And I'll give you some time to think about that. Okay, now you've had time because you paused. Okay, so what I came up with was the following, that we're going to consider these 4 edges, and that this one, and this one will all have their priorities updated. This one to 2, this one to 3, this one to 4. And the edge 2 array will be set up as follows. Okay? And here again, I've bolded these 2 positions to indicate that these 2 edges can definitely never change. This number and this number will never change. That's why these lines have a thick line. All right. So we continue along with the process. In this case, we're going to take vertex 1 next. Okay. That only has 1 edge going outgoing, and nothing happens. All right. Next up comes 3. So here's 3. It has 2 outgoing edges. Actually, it has 3 outgoing edges, but these 2 are already marked, so there's nothing to do. But this one, we see there is actually a better path. And so what we'll do then is reset the edge 2 value to 3, okay? Saying that we found something better. So before, the best we knew is we could get there from 4, but now we find there's actually a better way to connect up this one compared to this. Okay? Alrighty, next up comes 6. So when we relax all of its outgoing edges, we get this one. That ends up being best. And so now we have locked in all of these edges here. And then finally we'll relax 5, and now we're done. Okay, so that's Prim's algorithm in terms of specific data structures, but what I've just described here is the same as that easier to understand demo we had right here. Okay, so why does that work, right? Why does that algorithm work? Well, I think the easiest way is to look back at this intuitive demo we did before and to recognize that at any point in the process, that whenever we have drawn a cut with gray and white arrows, that we're always adopting the edge which has minimum crossing weight, so we know it's good. Okay, so let's do some comparing and contrasting of Prim's and Dijkstra's algorithm. On the left, I'm going to start out Prim's algorithm, and on the right will be Dijkstra's from the same source. Now what we'll note is that they both have this sort of creeping growth feeling. Dijkstra's algorithm crawls this entire graph, spreading outwards from a central point because we're trying to find the shortest path from the source to every other point. And then on this side we have Prim's algorithm, which is finding the closest the closest vertex of the entire tree at any given time. So it's always growing outwards, but it can jump around a little. So right now it's following this path. Okay, la la la. All right, having a fun time. Okay, oh, but you see it jumps around a little. Now it's exploring different places. Okay, but in every case, what you're getting is the smallest edge that's connected to everything. Okay? And so we end up with, when they're both done, totally different trees. This tree is spread out from a central point, and this is the tree that connects everything up together. Okay. So what I'm going to make an observation is that Prim's and Dijkstra's algorithms, I just kind of said this stuff, but that the difference between the 2 algorithms is that Dijkstra's visits vertices in the order of their distance from the source, right? Whereas Prim's algorithm visits vertices in order of the distance from the minimum spanning tree that we're currently constructing. Okay? And then there's a slight difference in terms of the edge visitation. When we visit a vertex in Dijkstra's algorithm, that means we're going to relax all of its edges. And in Prim's algorithm, it's the same thing. We're still relaxing all of its edges. But what we're going to do in this case is use the metric of distance from the tree instead of distance from the source, as we saw. We're always just looking at the size of the edge, not the entire path from the distance to the source. So that's Prim's. And so we can write up some code, and I'm not going to focus in on a lecture. But if you want, this is a good pseudocode implementation that's pretty honest, and it shows you what you end up getting if you run, or if you were to try and write this up. So we have a bunch of data structures that reflect what we saw in the demo video, and we have basically a main loop here that just says keep deleting vertices until it's empty, and each time you get to a vertex, we're going to scan that vertex. And what does scanning mean? Well, it means mark it as true, that is color it white. Then for each edge, look at the other side of the edge. If it's already been marked, don't do anything. However, if the weight of the edge is best than the best known distance, then set the distance, set the edge to, and then adjust the priorities as necessary. So if it's a vertex we've already seen, we'll add it to the priority queue. If it's something that we already have but it has a new weight, we'll change its value. So if you want, you can compare this code to the process that you carried out by hand. We had that little exercise in the middle of the explanation of the algorithm. Okay? But I don't expect you to understand this code deeply. I more want you to get the big picture for this algorithm, because I don't want to get too heavy-duty into programming. Okay? Now here's a really challenging problem for you, which is to consider the runtime of Prim's algorithm. And here's the code. Okay? So think about that a little bit. Okay. I'd say it's a pretty hard problem. And so what you're going to want to do is count up just the runtime of each line, okay? And to think about how big the queue could get, or the fringe. All right. So let's do a spoiler here, and I'll just give it away. And I'll say that the runtime for prims is actually exactly like Dijkstra's runtime, which we did move through pretty quickly. And the basic idea is that we're ultimately going to need to insert all of the vertices at some point. And each of those insertions, because we have a priority queue, is going to be log v time. Likewise, each vertex gets deleted exactly one time, and what we can say is that certainly it's going to be no more than log v, right? The hardest delete is if everybody's in the priority queue and you're deleting one. So log v is the worst it could ever be. And then finally we have up to e decreased priority operations. That is, each edge, whenever it becomes purple, magenta, right, when it's being considered, each edge may cause a priority decrease, which is where we cross out the number and put in a new value. And each of those values, each of those decrease in priority operations is going to be log v time. Okay? Now, as I believe I mentioned in the Dijkstra's lecture, but I'm not certain, the lab in which you built a priority queue which had a decreased priority operation, you might have observed that your decreased priority operation was linear time, whereas this decreased priority is log v time. And so what we're using is a slightly different version of a priority queue we have not discussed in class that has the special feature that it can adjust priorities in log v time, and it works by avoiding the step of having to look up the item in question, which we want to decrease the priority. How do we do that? Well, we'll take advantage of, I don't have a good picture for it, but we'll take advantage of the fact that the vertices are numbered 0 through v minus 1, so we can index directly into the priority, but I don't want to get into it so much here. So in this case, I'm going to assume that e is bigger than v, so the real runtime for this algorithm would be v log v plus v log v plus e log v, but because e is bigger than v, that just works out to e log v. Okay? So maybe just slightly differently put, if we look at each of the priority queue operations, they happen v, v, and e times respectively, and the amount of time each takes is log v. And so the total time for each type of operation is v log v, v log v, e log v, and if you sum all these, because e is bigger than v, you get e log v overall. Okay? So that's the runtime of our Prim's algorithm. Now you may say, why were you focusing on the priority queue operations? Why not adj? Why not marked array setting? And it so happens that if you look carefully at the code, and it takes a lot of thought and some deep inspection, you'll convince yourself that the priority queue is going to be the bottleneck. Okay? But really, if you wanted to be totally honest, we might list other things here as well, but I happen to know that the priority queue is going to be the bottleneck. Okay? So this is a pretty challenging runtime problem, and it definitely will be on the harder side, the kind of runtime that we would expect from you. All right. So one more algorithm to discuss, Kruskal's algorithm. Maybe take a chance to stretch your legs and think, because really what we've just done, I mean, it's pretty heavy duty, right? We move pretty quickly. Understanding these data structures and understanding these runtimes, they probably should seem hard, but I hope that by the time that we're finishing out the semester, this should be close to comfortable at least.